So, very good evening and welcome to yet another exciting episode of Physics for Students. I am your host, Shaunak, and today we have a truly special treat in store for you. We are about to embark on a journey into the mysterious and captivating realms of quantum field theory, cosmology, and more. Our guest speaker today is not only a distinguished scholar but an expert in the field. Professor Sayantan Chowdhury is a renowned physicist whose work has left an indelible mark on our understanding of the universe's fundamental building blocks and the grand tapestry of cosmic evolution. But it is not just his impressive credentials that make today's episode special. Professor Chowdhury has a unique gift for making complex concepts accessible to all, from students to seasoned physicists. He had a passion for sharing his knowledge and insights, making him a perfect guest for Physics for Students. Professor Chowdhury has research experience of more than 8 years after his PhD in the branch of theoretical cosmology, quantum information, aspects of gravity, quantum field theory and curve space, and a lot. He has mentored more than 5 MSc students and more than a huge number of MSc, PhD, and he is now the peer reviewer of more than 45 international peer-reviewed journals and is associated with the editorial boards of 4 journals. Recently, I congratulate Professor Chowdhury for being the member of the National Academy of Sciences, Nasi, Prayagraj, India. He is also researching on a very interesting topic which I am eager to hear, nanogram. So without further ado, let us welcome Professor Sayantan Chowdhury to Physics for Students and dive headfirst into the mesmerizing world of quantum field theory and cosmology. And I would like to welcome Professor Chowdhury. Thank you very much for joining us today.
Thank you, Shaunak, for extremely elaborated and nice introduction. I don't know how much thanks to you.
No, you're welcome, sir. You're welcome. Sir, my first question to you would be because your area is huge, your expanse is huge. So with the all the people who are joining today, we are willing to learn a lot from you. So we already got Rohit Gupta saying that, hello, welcome, sir. So my
Thank you,
question, sir, yeah. So my question, sir, first would be that why is quantum field theory so important as a field of research in today's world, and how it is evolving? If you can just throw some light.
So I have to say, this is a very good question you have asked. So, quantum field theory is a language. So,
Okay.
without the language, any subject is incomplete. So, if you are interested in high energy physics, theoretical high energy physics, I have to say these days in low energy physics as well, means condensed matter physics. Quantum field theory techniques, tools are extremely important. Modernized techniques, old techniques, even, okay. And particularly after inventing this particular phenomena called path integral approach of quantum field theory, things become very important. So before, mostly high energy physicists use this tool to calculate the scattering amplitudes, estimate things from different processes, and try to check whether these things are compatible with the colliders, etc. or not. These days, it is not restricted to that only. These techniques used by the people, those who are doing cosmology, those who are doing condensed matter physics, uh, quantum gravity theory, string theory, everywhere these techniques are right now people are using. So my point is, this is the language. So without the language, we are completely uh, we don't know what to do. So everybody should learn quantum field theory.
That's wonderful. Thank you very much, sir. So, as you have rightly told, and I expressed this idea in one of my videos, that mathematics, even my father, as I was telling you, is from IIT Kanpur. He always tells that mathematics is a language. So, if you learn the language in the form of language, then mathematics is not so difficult what you really think. Sir,
See,
this actually, yeah.
see. You have asked me, look at my cup. This is also quantum theory. So
Okay.
this
Can
is,
you just bring it to the camera in front a little bit, sir? That's
yeah,
wonderful. Okay.
this is the
Okay.
cup gifted by ICTP Trieste, Italy. And this is the
Okay.
whole Lagrangian of the universe.
Ranjan, the standard model.
Standard model including gravity.
Oh,
Okay.
including gravity. Okay.
Usually people don't write gravity in the standard model, but
Gravity. Right, right, right,
they have written that. So see,
right.
everywhere.
Absolutely, sir. Um, I have one question already coming in. As I told you, there are many people would be joining today. So Aru Verma is asking, sir, I have a doubt. It may sound stupid, but can we trap a photon in a box? If we can, what will happen after trillions years later? Can you please explain, sir?
Uh, so, wait a minute. Trapping a photon inside a box. I think this is possible, but I'm not very sure what is the outcome in trillion years later. Uh, I'm not very sure about the outcome. Sorry for that. I have to little bit
But
think about that.
trapping is possible.
I think trapping is possible.
Okay, okay. Sir, actually, you were talking about the path integral formalism. I think that as Richard Feynman's contribution, that it is not only one single path that a particle is traveling, we actually have to take all the things
So,
together. And yeah.
yeah.
So, sir, yeah, we have read that, but if you can just explain it in a simple language and why it actually revolutionized quantum field theory, the path integral formalism, we would like to hear from you, sir.
Yeah, so this path integral formalism basically um, uh, it's a formalism which basically takes care of the all possible paths starting from an initial point to final point. So you have to integrate over all possible contribution, all possible trajectories, and after integrating over all the trajectories, the only information contained in the quantity whatever you are calculating is basically the initial and the final point. And in quantum field theory, particularly where we do the perturbation theories, mostly initial and final point informations are important because that directly goes to something called amplitudes. So amplitudes, which is a fundamental quantity within the context of quantum field theory, basically made up of some initial states and the final states. So these contribution can be directly understood in the language of path integral very easily. And after that, this goes to something called Schwinger-Dyson series. If you write down the Schwinger-Dyson series, you will see that uh, each of the contribution appearing in the order, each order of the perturbation theory, basically made up of all of these initial and final states. So if you have just only the information of the initial state and the final state, you can able to construct the whole information out of this calculation. But yeah, uh, till now we don't have any understanding in between what is happening, means the instantaneous information of the states. If somebody can able to do that, then it would be excellent, means till now we don't have any access to that type of calculation. So to add, we means I and all my few of my students, we are trying to understand if this is possible, and we have I actually have done this type of calculation that if we can able to access the instantaneous information of this type of processes, means what happens in some arbitrary time what is the situation of the states, what are the things we can able to understand in terms of a quantum field theory system. Is it really useful, or it's just kind of some calculation? We are trying to understand that. So Feynman's contribution not only restricted to just calculating the path integral here, but there is a guy called Varnon. In 1968, they have proposed a remarkable formulation which basically helps you to write down the path integral when you have a dissipation, quantum
Okay.
dissipation. We know that how to write down action, how to write down equation of motion for a harmonic oscillator. But
Right.
if you ask some students, write down the equation of motion for a damped vibration or a forced vibration after varying the action. So writing down the action for forced vibration and damped vibration is not very easy. So this idea was proposed by Vernon and Feynman in 1968.
Okay.
This idea was further adopted by Caldera-Leggett to formulate
Okay.
the theory of quantum Brownian motion. So
Quantum.
this is the
Okay.
fundamental of quantum Brownian motion. And then the classical idea means
Right.
whatever Brownian motion we know that came from that later. Means
That
it's a
means, sir,
little
right. I was also studying like Lagrangian and Hamiltonian principle of least action. I was reading a book where it starts from Snell's law, why the path of the light will be slow. From there, Pierre de Fermat's format. So
this,
Lagrangian and
this is basically principle of least action.
principle. Why this principle of least action is very much related to quantum field theory. Can you throw some light, sir, please?
Yeah, so as I have told that in quantum field theory, we have only access of the initial and the final states. And we don't need any information in between till now, whatever formulation we have in the perturbation regime. So we don't need any information in between the parts. We have to integrate over all possible contribution inside whatever happening from initial to final points. So
Right.
that's why. Uh, could you please repeat the question? You
Sir,
said.
I was repeating that why Lagrangian and Hamiltonian principle lift action is related
Yeah,
to
yeah.
quantum field theory.
So since here integrating out all the contribution in between both the initial and final points is basically you are taking into consideration that you are considering some kind of principle of least action, whatever we do in optics to
Optics,
calculate Snell's
absolutely,
law. Yeah, yeah.
absolutely.
This is
Snell's law,
huge
right,
one-to-one correspondence.
right. Sir, we already got questions coming up, so I have to shorten my discussion. So the
Hmm.
first question from Sanket Thakkar is, hello, sir. What are the challenges in cosmology can be explained by quantum field theory like dark energy or quintessence?
Very nice question, Sanket. Uh, Problem is it's a very big problem. Dark energy means you are talking about the universe at the present epoch. Uh, Unfortunately, the idea of quintessence is very good. It basically gives you some kind of scalar field model uh, in the late time, which explains the late time. Try to produce a correct equation of state parameter, which is a very fundamental quantity in dark energy. And if you assume that your model or whatever model you are using, it's almost cosmological constant dominated at the late time, then it is expect the equation of state parameter at the late time has to be of the order of -1 if it is vacuum dominated. But from the data, we found that the equation of state parameter is more negative than -1. Now, the problem is there is no fundamental theory in QFT which can able to explain this fallacy. It's a huge problem. Like people try to write down means enormous number of theories to explain this fallacy, Some people use something called like initially it was lambda CDM, then it goes to some more negative than -1 kind of theories. But like I don't know how much this is correct, but if you solely believe in quantum field theory, if you're a quantum field theory lover, from the quantum field theory perspective, I don't think so you can be able to explain the origin of dark energy at present completely. So you have to use a phenomenological model building in that case. These days, people also trying, there is something called artificial intelligence and machine learning techniques. Using that, people are trying to construct the equation of state and trying to construct various other important facts of dark energy. Um, this is a problem, really a problem. Another important thing, since you have asked, I just want to tell you, for early universe, we know that how the expansion of the universe happened. But the problem is for the late time, why this phenomenological model building is important, because we really don't know what is the exact form of the scale factor, how it is changing with time, how it is changing with the redshift. We really don't know. So we need to either parameterize the scale factor or the Hubble parameter, all these things. Hubble parameter is the rate of change of the scale factor. Otherwise, you have to design or engineer or phenomenologically construct a model which can able to explain this type of problematic situation. So for the timing, I can say that just completely relying on QFT, you can't do that.
Thank you, sir. I think, Sanket, you got your answer. And Pankaj is telling it is great to see Dr. Sayantan Chowdhury here. So thank you, Pankaj, for your comment. So the next question coming up from Serdar, I don't know if I'm pronouncing your name correctly. What does gauge theory mean?
Excellent question. Gauge theory is basically, so I can give you an example. So, like our electromagnetism. Our electromagnetism is a gauge theory. It's a gauge theory because uh, the fields, which is basically the fundamental object which is generating this photon degrees of freedom, it's not completely uh, free from the choices of any kind of arbitrariness in the theory. Means if you add a space-time dependent parameter and rescale your gauge field with that, you will see that that additional redundancy will change a lot of things inside the system. Now, if under this type of rescaling, if your theory is not invariant, then it is a very problematic situation. So if it is invariant and if your rescale parameter is space-time dependent, then you call it a local gauge theory. And if this scaling parameter is not space-time dependent, then you call it a global gauge theory. So any type of gauge theory actually helps you to write down a correct description of quantum field theory under this type of rescalings. So one of the example is electromagnetism. You can do this similar kind of thing is for gluon, which is basically one of the fundamental object for strong interactions. So electromagnetism, you know that photons. So photons is the fundamental objects for the electromagnetic interactions. So there also you can do that. So yeah, this is my point of view about gauge theory. And without understanding the gauge theory, the problem is uh, if you are again, I don't know means how many people are interested in quantum gravity theories. So some people usually say that gravity theory is an artifact of gauge theory. So it's sometimes you call it a gauge gravity duality.
Okay.
Whatever happening in the gauge theory side, it's similar in the gravity theory side. Just to extend one more thing, if the
Sure.
gauge theory is not there, then the problem is, um, like, yeah, what to say. Uh, in principle, we should know that what is the gauge group. Gauge group. This word I haven't used. Any gauge theory is associated with a symmetry group. Now, this if symmetry is not there inside a quantum field theory system, then you can't able to extract any kind of any information, because breaking of the symmetry helps you to extract information from a quantum field theoretic system. So this gauge group thing is very important. We still don't know what is the gauge group of gravity, but we have an idea of what is the gauge group of strong interactions, electroweak interactions, and yeah.
So, sir, you would be surprised that Serdar is joining us from Turkey and is very happy to receive the answer. Uh, Sir, the next question I have got again from Rohit Gupta, but Rohit, you have to wait. Don't take me wrong. There's another person who is asking, Shrish Sahai. Now,
Hmm.
he's asking that what is the relevance and future of classical black hole study in reference to PBH? Is there any research relevant to classical PBH and its local space time?
What is the relevance and future of classical black hole study in reference of PBH? Yeah, I think you can do. Um there are lots of things. So PBH is basically he's talking about black holes generated at early universe, primordial black hole.
Primordial black hole. Right,
Yeah.
absolutely.
So yeah, like classical black holes. Yeah, like the calculation etc. We do basically classically, means like if you I really don't understand what exactly you want to mean, but if you are asking that there is a future possibility references to PBH, I have to say there are huge remarkable possibility in this area to do research, um, particularly classical black hole perspective. Yeah, lots of thing you can actually study, means is there is any research relevant to classical PBH and its local space time research. Yeah, like people are doing these days a lot of calculation related to that, like how PBH is forming, what is the outcome of this kind of PBHs, whether that can able to helps you to formulate the dark matter or not. What is the like the PBH you are forming from a system, are you producing correctly, or it is you are producing like extreme amounts? People call it a overproduction. So can you able to address this issue of overproduction? Can you tell us that uh, how this PBHs are actually evaporating? Okay, so these are the things you can able to study, I believe, from this type of formulations. Though these PBHs are generated at the early universe, so seeds of this PBHs should be the quantum field theory. Okay, quantum fluctuations are the fundamental object which can able to generate this type of fluctuations. And most importantly, PBH is a kind of an object which basically generates from large quantum fluctuations. So large quantum fluctuations are extremely harmful for quantum field theory, because sometimes it pushes you to go to the non-perturbative regime. And
Non-perturbative. Yeah, that is very difficult to
and
solve.
if you want to work in a perturbative regime, then sometimes it happens that all the quantum corrections becoming large. So your perturbation theory is trying to break. So that's why these three papers here, probably you can see that I have written three papers. These papers actually was cited by this nanograph collaboration. So there we actually have pointed explicitly with the quantum field theory calculation that um, this large quantum fluctuations, how that can be treated within the framework of PBH formation. And we are doing a lot of work with students. They're working with me, and we are trying to understand these issues, whatever I am telling right now, like uh, whether the perturbation theory is valid. If it goes to the non-perturbative regime, then what happens? How to treat this perturbation in a very clever way so that you can able to get correct amount of PBH abundance. Is this compatible with the dark matter production? Are you producing things in a correct way, or like you are going in an overproduction regime? If you are going in an overproduction regime, then can you able to address this? A lot of things we are doing. So I think Shirish, a bit of you have asked a very broad question, but yeah, like these are the things I think you can able to do. But since you are a student, actually he is a student from our center only. Okay.
Okay.
So he did his, I think, bachelor's thesis here. So anyways, it's a nice question. Since you are a student, it will be helpful for you to do a lot of research out of this thing.
So Sanket Thakkar is asking another question. Path integral in quantum field theory is similar to variational principle in classical mechanics.
Path integral in the concept is like that, because you are basically integrating over all the informations of the like in between trajectories, trying to formulate a theory of initial state and the final state, which basically depends on the initial state and the final state. In variational principles also, once you do the variation, you basically use the principle of least action, which helps you to remove all the contribution in between, and you can able to get information of the only boundary points. Similar kind of
Okay.
similar kind of thing, similar kind of thing. One exception, there you basically integrate over uh, all the amplitudes which is scaled by h cross. So this is basically the taking care of the quantumness of the amplitude. In classical mechanics, you don't have any h cross, means the Planck's constant I'm talking about. So in classical mechanics, you can't able to do that. So it's kind of a averaging over all quantum trajectories, and this is basically averaging over all classical trajectories. This is the difference.
So Shatvik Roy has got a question. We know the Higgs field gives mass to the elementary particle. My question is, what gives the Higgs field? Gives rise to Higgs field? Can quantum field theory explain that?
What gives rise to Higgs field? He's asking the origin of the Higgs field.
Origin of Higgs field. Right, right.
Okay. Um, yeah, like I'm not very much expert in particle physics, but as far as I know, the uh, underlying symmetries are important to have this type of. So it's kind of a double. Higgs is basically kind of a doublet. Okay, doublet means it's kind of coming from SU2 symmetry. So SU2 symmetry, since it is tagged with a symmetry, obviously, without having this symmetry, this symmetry is there in the standard model. So SU2 is a symmetry which is the part of electroweak symmetry. So our standard model gauge group is SU2L cross U1Y and cross SU3C. Okay, so SU3 is corresponding to the QCD, strong interaction. SU2 is for the weak interaction, and U1 is for the electromagnetism. So SU2, to have this SU2, you need to have a structure like a Higgs field. Otherwise, you can't able to construct a standard model, which is basically a fundamental theory of elementary particles. And initially, once you construct, you will see that uh, uh, if you try to construct from a scalar field theory or something like that, you will see that the it's just a kind of a theory which having a mass and a self interaction. Now, if you break this symmetry spontaneously, then you can able to generate a kind of a reliable theory of Higgs having a kinetic term and a potential, and this potential contains uh, like one local minima, one local maxima, and two global minima. And if you rotate this Higgs potential, you will see kind of Mexican hat type of structure. So my point is, if you know the symmetry correctly, then you are coming with this type of structure, unique structure only. So I believe I have given the answer.
Absolutely, sir. Sir, my next question would be, this is a kind, I would say this is a misnomer, or I think that it is a kind of a, maybe a misconception which people mostly have about black holes. Now, you understand, sir, that the recent, I would say, popular science, because things are not always explained mathematically, they make a kind of a very romantic picture that this is black hole. If you dive into, you understand, sir. So I always try to tell my subscribers, students everywhere, that let us not fall into popular science, but let us find out the real truth. Now, today you are here. I would like to ask you one confusion which is quite common. That is, if we take a kind of a black hole, a strong gravitating mass, a particle falling, etc. Now, there is one thing which is called a stable orbit and an unstable orbit. Now, what is the probability, say, for example, if I am traveling to a black hole, that do I really fall into the black hole, hit the singularity, or I keep on going and going? Number one. And what is the mathematical, I would say, formulation that there is a wormhole and you really come out of another universe diving into the black hole? If you can have a, please explain few notions on that, sir.
So I think you were talking about. So best way to answer this thing is quantum entanglement.
Right,
I
sir.
believe.
Right, right,
So quantum entanglement is one of the strongest uh, thing at present. It's a kind of a technique again, without which you can't able to explain a lot of modern day concepts of quantum mechanics. And if you look into the earlier concepts like black hole, etc., particularly the quantum black holes, you can't able to explain a lot of things. Particularly, I want to point, there is something called, everybody knows this thing, it's a Hawking radiation,
right.
and related to that there is something called information loss paradox. Okay, so this is a very long standing issue, people try to solve in a different way, but in the end the present status turn out to, because you just talked about wormhole. Okay, so wormhole, people usually study in the GR community on wormhole, people study from the geometrical perspective. Okay, people try to construct like wormholes from symmetries, people try to construct metrics out of, by solving the partial differential equations of the Einstein equation, and trying to construct the space-time geometry, how it looks like. But if you want to study the fundamental phenomena related to wormhole, you have to have a access to quantum entanglement, because wormhole basically talks about two important concepts called ER and EPR. I don't know like how many people are aware of this thing. If you know a bit of quantum entanglement, then you may be aware of this thing. But this ER stands for the Einstein-Rosen, and EPR is Einstein-Podolsky-Rosen. Now they are same. What is the meaning of that? Like how to show you? I can able to show this.
Sure, sir, sure.
So suppose you have a space-time kind of a this. So you are going from here, and so suppose you have a kind of a black hole type of thing here. It's a space-time sheet. It's bended like that, but you can go from this point to that point by this way, or you can directly go from this point to this point by putting a tunnel inside that. So if you are going inside and if you are going outside, so there is a possibility, like people used to say that maybe there is a time lag, or maybe there's some information is losing. But the thing is, if you are really considering the construction with the help of quantum entanglement, then you can able to explain that both of the information actually gives you the same thing at the next in the end of the day. Like suppose you are constructing a state here. Suppose you are constructing a state here. Now the combination of those both of these states, the entangled states, will give you the same amount of entropy if you go like this and if you go like that. So these entropy I'm talking about, the quantum entanglement entropy, which is basically measured by von Neumann entropy, minus trace rho log rho, where rho is the density matrix associated with this kind of computation. So this density matrix you can able to construct. Rather, I have to call it a reduced density matrix. You can able to construct if you know the information of the states. And these states is basically the subsystem states, which is basically can be made up of by taking the partial trace over all the possible states available in this construction. So you can able to do that. Shaunak actually asked me regarding this wormhole. So my point is, without having an access to and proper understanding of quantum information theory, correctly telling about black hole is just it's not correct. It will turn out to be kind of a philosophical or maybe
philosophical interpretation, right?
So quantum information theory is the ultimate frontier, I have to say that. If you are
So
really
Navneet Mishra is telling, sir, awesome explanation, because you folded that. So, sir, what I was trying to make a point is that the body really falls inside the black hole or keeps on rotating forever?
I think you just can't access inside the black hole like that. Okay, even what exactly happening, I am actually not believer of this kind of whatever melodramatic science. Okay,
right.
or maybe this interstellar wala science, what
right.
kind of science. But as far as I know, you can't directly have an access inside the black hole.
Absolutely.
Okay, if you have access, then you can able to tell now what is going to happen.
What is going on? Right.
You
Absolutely.
can't. That is impossible. Yeah.
Sir, Rohit is asking, in new inflationary model, Andrew Linde is driven by scalar fields. Is Higgs fields driven by same scalar field or something different?
In new inflationary model is driven by scalar field is Higgs field. Driven by same scalar field or different. What is the question, Rohit? Could you please explain? It's very confusing.
Rohit, you need to write it once more. I was also not clear. I will go to the next question by Manojit, a very old subscriber of mine. Is it possible to understand quantum spin physically? I mean, I think he's taking that physical measurement. Or is it arises just because of Dirac's perception of relativistic quantum mechanics?
Is it possible to understand quantum spin physically? What is the means measurement kind of thing he's talking about?
I think, is it a measurement, or we can actually experiment, feel, or see anything like a spin or something like that? Or is it pure mathematical?
No. Like one is basically thing is basically called intrinsic spin, and another one is a spin associated with the angular momentum. Angular momentum you can able to access because of the
Access, right?
rotation, because of the
Absolutely.
rotation. So if you have a system, which, suppose you are designing a system inside a lab, you are trying to understand its some kind of rotational symmetries, etc. There in classically you can able to have an access to this parameter called spin from this angular momentum. Okay,
Right.
but if you are really interested to know about the intrinsic spin associated with the system, with that you can't. That you can't. To explain that, you need to go this relativistic quantum description of Dirac.
Right. So you got the answer, Manojit, that intrinsic spin.
Maybe in some of the cases, as far as I can remember, uh, in some of the cases in the long relativistic limits, you can able to calculate some of the special quantities. One is called uh, one is called helicity, I think. But helicity is also associated. Probably, I'm not. I couldn't able to remember correctly, but there are two parameters which is basically associated with this kind of description. One is called helicity, another one is chirality.
Right.
Okay. For massless object, these helicities and chiralities, both of them are same. Helicities is basically the projection of the linear momentum in a particular plane kind of thing, and chirality is basically made up of particularly whatever he is saying, relativistic quantum mechanics. It's called uh, a matrix which is related to Clifford algebra. It's called gamma 5. Okay, so relativistic quantum description is very important to describe this intrinsic spin wala thing. But if you are really interested to know about this orbital angular momentum and associated symmetries and the quantities attached with that, I think you can able to do that inside the lab. Means from the real world visualization perspective, you can able to measure that.
Sir, before we take any question, I would like to, first of all, those who are joining late, it is an incredible discussion that we are having with Professor Sayantan Chowdhury. Sir, if you can explain what is nanograv, the research that you're going. I saw that on arxiv.org you has already submitted quite a number of papers. So we are all excited to know about nanograv. And then we have got Success Boy, Time Travelers, and even Rohit Gupta's question. So I would request to stay for a few more minutes, all the subscribers, and disturbing Professor Chowdhury. Sir, if you can just explain a little bit on nanograv.
Yeah, that's a nice question. Nanograv is basically recently in huge hype. So nanograv detected a signal of gravitational wave. First of all, I have to tell what is the full form of nanograv. Nanograv is North American Nanohertz Observatory for Gravitational Waves, and it is a part of the collaboration of something called pulsar timing arrays (PTA). Nanograv is actually running within the frequency range 10 to the power minus 9 to 10 to the power minus 7 hertz. And if you work out a bit, you can able to show that it is basically accessing the wave number corresponds to 10 to the power 6 to 10 to the power 8 megaparsec inverse. Megaparsec is basically a very fundamental unit in the context of cosmology. And yeah, so this is our nanograv. Nanograv actually, it's a they are collecting the data from uh, three experiments, which is called Green Bank, which is happening in Virginia, a very large array which is happening at Mexico, and there is another one is which is I think Arcibo or something like that, which is happening in Chile. So they are collecting the data together and trying to get information of this stochastic gravitational wave background. And recently, the data tells us that within this frequency range 10 to the power minus 9 to 10 to the power minus 7 hertz, there is a amplitude, there is a peak they have observed uh, in the gravitational waves abundance plot. Now, this is very important from the perspective of theory, those who are doing theoretical cosmology and etc. Because we have a lot of theories coming from the early universe, but the point is we really don't know what is the source of this type of stochastic gravitational wave background. Now, there, if you really go to the deeper level of the theory, we can able to understand these signals may be coming from primordial gravitational waves, or maybe coming from first order phase transitions, or maybe coming from cosmic strings, or maybe coming from topological defects, and so on. We don't know which one is the correct one. So, if you are talking about primordial gravitational wave, primordial black holes, particularly, there comes the role of a very fundamental thing called inflation. So, inflation basically generates the quantum fluctuations at very early universe, and that fluctuations basically grows with time, and at a particular scale you can see that the amplitude of this fluctuation rises and basically give rise to the generation of primordial black holes. uh, the amplitude is large. I have told you a little bit before that the amplitude is large, so it is very much problematic to handle this type of quantum fluctuations very crudely at the calculational level. We tried to understand this calculation deeply. Particularly, I have uh, introduced few techniques which is very well known in the context of quantum field theory, but in this context it is not very well known. I have introduced some kind of theoretical techniques for which is basically removing the contribution of the infinities, and this
Right.
particular technique is called renormalization. Okay, and additionally, I have introduced something called resummation, means correctly summing up all the correct information together and give a result which is valid at the classical level as well. So this is basically the resummation. So we means I and with my collaborator we did the calculation and found out that if you did this calculation very correctly, then you can remove this unwanted divergences which is called ultraviolet divergences, quadratic divergences from the theory, and you can able to construct a trustable quantum field theory description of the primordial black hole formation. So that's why Nanograph in their data releasing paper written a section on primordial black hole and devoted to write about something whatever we did in these papers. Like, yeah, here I have pointed few archive numbers. If any of the uh, so any of you are interested, then you can able to check whatever we did, and we are actually doing a lot of research out of that, and we are trying to understand that is this the conclusion that I have drawn is okay. I'm just stretching a bit because
Yeah,
since
sure,
we
sure.
yeah, since we are doing quantum field theory, so in the case of this removal of infinities, it's basically dependent on a lot of new schemes and techniques. We have used something called late time renormalization and adiabatic renormalization, or wave function renormalization. There are many more techniques available, like some people call it a minimal substitution and minimal substitution technique, MS bar, algebraic renormalization, and there are many more actually, dimensional renormalization, etc. So we haven't used the rest of the techniques yet. It's very difficult to construct even. We are trying to understand right now that if other techniques, if you can able to implement in this kind of calculation, then can you able to get the similar kind of conclusion? Can you able to remove these divergences very safely? Can you able to construct a very trustable quantum theory of primordial fluctuation, which can able to generate primordial black holes? And can you able to push this theory to the classical level, so that can anybody can able to measure out of this kind of calculation through resummation? So this is we are at present doing. It's a very involving task, and another important reason that Shaunak pointed this nanograv. So nanograv not only cited our work because of this techniques, we actually come up with a Nogo theorem. So this Nogo theorem tells you that if you trust our calculation, then you can't able to generate large mass primordial black holes.
Okay.
You can able to generate only 10 to the power 2 gram black holes, which is very small.
Very small, right? Okay.
So that's a huge challenge. Okay. You are going again.
Wish you all the best, because this is really an incredible, and I think that years to come we will see you more into this, because when I read about nanograph, because you sent me already the papers from ARXIV, so it was very puzzling, because the mathematics is quite complex. What I understood is that it is something related to cosmology, something related to the fundamental questions that we are facing in terms of physics. And I think, sir, with your kind of a talent and the huge student base, which I think they are all watching this, and the type of love that you get, I'm sure, sir, you're going to, achieve.
Since this is a common platform, I have to thank my all students, those who take part in this journey, helped me, all the collaborators, all my mentors, and my supervisor, and all the institutions. They helped me to grow like this. I have to thank all of them from the core of my heart.
Sir, one question. This
Thank you
nanogram.
for giving me this opportunity to thank
No,
them.
no, sir. This is my pleasure. This is my pleasure. You are with us. That is my pleasure. Sir, one thing is that the entire research of nanograph that you are doing, is it purely mathematical, or in the accelerator or something we can watch it or something?
No, it's a theoretical, but I can't say mathematical, because I don't do the data analysis part. Okay. We theoretician have some sort of access to the data, and we try to understand from our theories that whether our theory is compatible with the whatever we see. Now you can push forward a bit, like you can do kind of model comparison kind of thing, which sometimes cosmologists, particle physicists do. It's a kind of a statistical analysis. Okay, so which model is good? So to do that, people use something called Markov chain Monte Carlo. Okay, so doing this Markov chain Monte Carlo, people used to get some kind of information, and this information in statistics is called Bayesian factor. Okay. This Bayesian factor, if it is high, then sometimes people believe your theory because that is statistically more correct.
That means it is a mark. It is a sign that whether it is going in this direction or that direction. Right.
Fine. So we theoretician, I don't do that thing, but like there are lots of cosmologists and theoreticians do that thing, that part. I try to develop from the fundamental theory. Can you able to construct the whole thing so that you can able to match with nanograph? So that journey through our calculation we do.
Okay. Sir, we have a few questions. People are waiting. This is Laimayum Brajala. And what he is asking is that, sir, how do we get the power spectrum of the CMB?
Gate. What is the meaning of gate? Anyways, if I understood correctly, CMB is basically capturing the. So CMB is kind of a like last like point wherever up to which we can able to probe from like our present universe, beyond which we can't able to probe. So this is basically capturing the information of all the photons, and this is basically called the last scattering surface. And if you see the distribution of this, you will see that some of them are appearing with red, as some of them are appearing with blue. So this distribution is almost Gaussian. And if you correctly understood this kind of distribution, it is basically exactly matching with the black body power spectrum, having a peak at 2.73 Kelvin. So CMB has a huge kind of a CMB is basically kind of a black body spectrum. It's a manifestation of black body spectrum, and without understanding the CMB spectrum correctly, we can't able to tell anything about the early universe, because CMB spectrum basically contains three information. One is the basically the information regarding the scalar temperature anisotropy, which basically made up of the scalar fluctuations. Another one is the polarization, which is basically made up of the E and B, electric and magnetic polarizations and their cross couplings. Uh, if you are really interested to know what is the exact origin of our universe, then from that theory, if you can't able to understand the CMB spectrum, then that doesn't mean actually anything. So matching the CMB spectrum in is very extremely important if you are interested to construct a correct theory of early universe. And as far as I know, the correct amplitude for this purpose is 10 to the power minus 5. And this basically matches with the black body spectrum at temperature 2.73 Kelvin.
Right. Sir, thank you. Rohit is asking, sir, your project quantum aspect of space-time and matter is still going on. How one can join?
It's not my project, it's a forum, first of all. And I used to organize a lot of talks given by various experts. For that, you have to wait a bit, Rohit, because I am going to start it again. And I used to organize 2 talks per week, which I will organize independently, and a lot of experts from various parts of the world will give that talk. And if you are interested to work with me, then you have to directly write to me with your CV. That's the procedure, I think. And I think if you want to join the Facebook uh, group, then you just have we have a questionnaire. You have to fill it up and send me the request. I will check it. I don't know which
Right.
one you are talking about. That these are the 3 possibilities.
Right. So, sir, we have few more questions. I know it is getting a little bit longer. Before I take the question, just want to inform those who are watching it that we are in a fantastic talk with Professor Sayantan Chowdhury, starting from quantum field theory, cosmology, etc., which you're watching directly on my channel, Physics for Students. And in the month of October, I am yet to reveal the surprise. I have got a very famous person from the area of nuclear physics will be joining directly from the University of Oxford. Is there in London, done his studies in University of Cambridge. So stay tuned. October end, I will announce the date as soon as October starts. Whatever are your questions on nuclear physics, positron, electron, etc., a very senior person from the University of Oxford would be joining us. So stay tuned. Now, sir, this is a question. I hope you won't get angry, but somebody called Success Boys is waiting for that time. I know that you might say this is not a mathematical question, but any question I think should be appreciated. Is asking, sir, what is time? Is there any end of time?
Okay. Uh, it's nice question. I don't know what to say, but there is an end of time. If you know that where is the end of our space time, then we also know that what is the end of time. So, like the universe we are living, if it ends, then your time also ends, I believe. Now, I don't know that which philosophical perspective you have asked this question, but uh, if you understand time as a space time concept, then You can't just separately talk about time. It's basically a space-time thing attached with each other. It's a kind of a coordinate, so you can't say that it's end of time or something like that. I think you have asked from the different perspective, which is our clock time. Okay, if you are asking like that perspective, I really don't know what to say. I really don't know what to say. But from the space-time perspective, the answer is, if our universe collapses at some point, and then that would basically decides the end of time.
Right.
Okay.
Thank you, sir. Thank you very much. Sir, Rocky is asking, how can we get into AEI Max Planck Gravitational Institute after MSc? With MSc thesis, can we apply or we need to give any examination?
Okay, so Albert Einstein Institute, Max Planck Gravity, Potsdam, Hanover, both. As far as I know, there is something called IMPRS program. So IMPRS program, you have to apply through the portal, and you have to also mention that in which area you are interested in, because as far as I know that in each year they have some kind of uh, preference. So you have to mention the preference, and sometimes they clearly mention that they will take students for the gravitational waves, or they will take students from the quantum gravity, or etc., etc. And you have to write a person from the institute with whom you want to work with your CV and etc., etc., details, whatever details you have. You have to write with your CV and master's thesis to that guy for your support. Now, parallelly, you will apply, and they will ask you for the recommendation letters. I think they will ask you 2 to 3 recommendation letters that you have to send. And if they believe, it's not always same, if they believe you need a, because when I was there, they did once, they asked the candidate to come and give a interview. No written exam, but give an interview. So it depends on the committee and the year and their perspectives. I think this is clear to you.
Thank you, sir. Sir, before we wrap up, I will just don't disappoint anybody. Just quick questions. Manojit is asking, what is the source of gravitational wave? Is it a disturbance of space-time curvature?
Yes, space time. You yes means curvature means yes. You are right. It's a artifact of perturbation. Okay, once you perturb the space time, your metric basically, I call it metric is the fundamental object than the curvature, because curvature can be calculated in terms of metric. So if you perturb the metric, this metric perturbation can be decomposed into scalar, vector, tensor. This tensor perturbation is the source for the gravitational waves, and these gravitational waves, in principle, you can understand classically, but if you really want to understand the origin of the gravitational waves, and like role of the fabrics of the space-time and the fundamental origin, how this is related to the gravitational wave perturbation, then you really have to quantize gravity. But the problem is you don't know how to quantize gravity. That's
It's
the
gravity.
that's the main problem. We don't know how to quantize gravity, so we try to understand this problem semi-classically. Okay, we don't quantize the full description of the gravity, but we treat it kind of partially quantization. And anyways, here two question comes, like, to construct a correct description of quantum gravity theory, which I believe till now also string theory. And another one is basically to understand with this semi-classical description how one can able to understand the origin of the early universe. So two things you
Yeah.
can able to study.
Sir, I have got another question from Rakesh. But before that, sir, one quick thing I want to ask. We know and we have heard and went through a lot of Professor Leonard Susskind's lectures on string theory,
Excellent,
quantum
excellent.
mechanics.
Yes.
Excellent. But my question, sir, is that some people say that Professor Leonard Susskind is considered to be the father of string theory. What is his actual contribution in terms of string theory?
Okay. As far as I know that He's some of the conjectures of the quantum black holes are the pioneering work in string theory. He with Professor Juan Maldacena, they have formed some paradigm which is called MPRS, and this MPRS is basically a very important uh, contribution in the quantum black hole physics. Apart from that, he's one of the fundamental contribution is basically understanding quantum black holes in the language of quantum information theory. This is the second
Okay.
contribution. Third contribution is how these quantum black holes are related to the fundamental matter, the condensed matter physics. So this is like some people used to call it ADS-CMT correspondence, means
Right.
anti-de Sitter condensed matter theory correspondence.
Right.
So he tried to understand whether the phenomena of quantum chaos can be understood in terms of quantum black holes or not. These are actually a remarkable thing. Means,
Remarkable. Right.
I actually met him like when I
Oh,
was
really? Okay. What was the experience, sir?
Remarkable. I can't able to explain by words. So I was there in Stanford for some visit I had.
So two quick questions and then they will end the session. Rakesh is asking what energy is being converted to emission of gravitational waves? Is it the mass of each binary being emitted as gravitational waves? Please do shine on this, please. Thank you.
What energy is being converted to emission of gravitational waves? Rocky, are you talking about the black hole binary mergers? I really don't understand what you exactly want to mean. Means if you are talking about the inspiral and then merger of the two black holes, then I think you are talking about the mass is the fundamental quantity which basically
Yeah, he is telling yes, sir.
yes. So then basically mass is the quantity through which. But another important thing, Rocky. So like things are improving day by day. So here also people do uh, very good to get a correct information. People do order by order approximation, because once two black holes are rotating around each other, this kind of calculation whatever we do it's correct. But if they are coming very close to each other, um Shauna pointed there is a phenomena called strong gravity, and because of strong gravity all this calculation fails. Then there is a technique called numerical relativity. So numerical relativity actually helps you to gather information when these two points are very closer to each other and gravity is extremely strong. Okay, so your thing, whatever you have said, the gravitational wave, it is correct if it is a little bit far from each other. But if it is very closer, you can't able to do this type of calculation. Then you have to go for numerical relativity.
Sir,
Okay.
again, yeah. Again, last two questions, sir. This is something I think you won't be happy. Mark is asking, what is your epistemological view on mathematics?
No, I believe without mathematics, physics is incomplete. As a theoretical physicist, my strong belief I think a lot of people will be angry after listening to this. Okay, but for me, without mathematics, physics is incomplete. Okay, and for me, mathematics is just not an equation or something like group theory or something like solving differential equation. For me, mathematics is a proper philosophy which basically connects you to the correct understanding of your universe.
That's wonderful.
Okay.
Sir, if you may permit one more question, Rohit is asking, sir, wormhole and entanglement are related. What is Susskind-Maldacena conjecture?
Rohit, I am not going to that thing because that will go into the deeper thing of quantum gravity. But
Gravity.
I will just tell you to look into this MPRS that AMPS, I think MPRS I have told wrong. called Am's paradox or something like that. So you just look into that. Yes, wormhole and entanglement, if you are trying to understand from the quantum field theory perspective, they are exactly connected to each other, correlated to each other. Without understanding quantum entanglement, you can't understand wormhole. So you
Right.
please look into the Susskind's and Maldacina's paper if you are really interested to that. And if you are really interested to know more about all these things, you can write to me personally. I can tell you.
I think that is better. Last question, user, somebody is asking, is pure mathematics important for physics?
Extremely important if you are really want to understand what is exactly going on.
Okay. So, sir, last, what is your advice in taking up quantum field theory as a career in further research? What would you subject? What level of mathematics and any books or the process that you would just frame in a few minutes to all the users who are watching and maybe who will watch later live? If somebody wants to take up quantum field theory, and I'm sure after listening to your wonderful motivating discussion, there are a lot of people, young people who wants to take up quantum field theory, what would be your advice in terms of mathematics? What is the knowledge, solid foundation is required, and what is the process?
Yes, it's a very important question for students, those who want to pursue research in this area. So, uh, my point of view to hit this kind of area is like try to do calculation and understand things properly, uh, and things will not happen in a single day. Okay,
Yes.
so you have to go step by step. So, for that, to understand quantum field theory, you have to start something called group theory. A lot of people I have talked don't know group theory properly. Why I am talking about group theory? Because group theory is associated with symmetries in quantum mechanics and quantum field theories. And if you don't understand the symmetries, how you can able to understand your nature correctly? Okay, so everything is coming up out of symmetries. So first of all, you need to understand discrete groups. Discrete groups are important, some sort of, and this is important in high energy physics as well as in condensed matter physics both. And particularly Lie groups are very important in some of the aspects of condensed matter physics and mostly in high energy physics. Okay, so group theory and books I have to tell. So there is a book by Howard Georgi.
Okay.
It's on Lie groups. I would suggest everyone to read that book. For discrete group, you should study. There is a book called Morton Hammermesh. Okay, and if you are an Indian supporter of Indian books or something like that, then there is a book by A.W. Joshi. Okay, so that is also very good book in group theory. So three books in group theory you have to understand, at least to start with the basic level of quantum field theories. Then there are lots of good literature in quantum field theory, because this is a, as I have told in my starting first minute of this interview, that this is the language, and without
Yes.
understanding the language you can't do anything.
Right.
So there are lots of good books. I have to start with, there is a since we are Bengali in the end, and there is a very good book by Palash Baron Pal and Amitabh Lahiri. It's a very basic book written for the college students, and can be understood by, I believe, everyone. If you are a little bit like know the basic stuffs, it's from Narosa Publishers. Okay, a bit better means those who know the basics. Then you can go for Michael Peshkin Schroeder. There is a book. Then there is a book by uh, a lot of people don't like, but I will say that is a good book. Ashok Das, Quantum Field Theory, one which is basically the canonical quantization, another one is basically the path integral formulation of quantum field theory, and there is another one which is basically thermal field theory. So he had written 3 books in quantum field theory. Okay, it's basically coming from World Scientific. It's coming from World Scientific publication. Then there is a book by Itzigson Zubair. It's a little bit hard book, means calculation wise. Now it's going a little bit in hard direction if you are really interested to do a little bit of mathematics, etc. Then Mark Srednicki. There is a very good book on QFT written in a path integral formalism. So I love a book very much. It's called, I exactly forgot the name. It's written by Pierre Raymond. So I found that this is the base book if you really want to study the path integral formulation of quantum field theory. Okay, this is written everything in that book. And last but not the least, the father of all the books, Steven Weinberg, volume 1, volume 2, volume 3. Okay.
Absolutely.
Okay. And if you really want to know the basic point of view of quantum field theory in the present time, then you have to know there is something called, I haven't talked about Shonok. I have to mention this thing for the students at least for 2 minutes if you allow me.
Sure.
So I haven't told throughout my interview, there is something called open quantum field theory. The quantum field theory we have talked throughout our interview, it's called closed quantum field theory. Means our quantum field theory, the system is not talking to the environment. It's an adiabatic system. Now, if your system is start talking to the environment, then it's basically kind of noise signal kind of theory. Means you are trying to constructing a theory of quantum Brownian motion type of thing in the language of quantum field theory. So this is basically a system which I think a lot of people knows about this. This is called open quantum systems. Okay. In the open quantum system, formulating quantum field theory is an excessive complicated task. Okay, so Shaunak, we are also trying to understand that thing because I am doing a research on that. From the in the cosmology, if you want to use this kind of open quantum system, then what are the outcomes? So we are also doing this kind of calculation, and I believe since this is a growing subject, books are not available. You will see a lot of review articles, etc. And Weinberg last written a book called Modern Physics or Modern Quantum Mechanics. I forgot his last book. There he devoted one chapter on that. And if you want to know more about these references, you can write to me. I will definitely share my references with you.
Those who wants to write, please go to LinkedIn and type up Professor Sayantan Chowdhury. Even if you're connected with me in LinkedIn, you can find sir as one of my common friend. His phone number, his email ID is available. Sir is very cooperative. The first day when I called sir, he told that Shaunak, this is an amazing thing, and I agreed. I wholeheartedly thank sir that there is one question which I have to take, otherwise he will be very angry on me. So he's requesting, sir, please, this is the last question. And I promise Professor Chowdhury, it won't take much time. This is the last question, sir. Please take this question. What is quantum relativistic lateral spectrum neutral gratify device?
Yeah, I really don't know about this thing.
Yeah, I was also thinking in that way. Anyway, so thank you, sir. Thank you. From the entire community of physics for students, all the 22, 25 participants who came and joined. I really have no words. On the last 3 episodes, this is one of the best episodes, I think, and one of the most intriguing, learning mathematics and a lot into. And I think that if time permits and if you allow, I think we can again host you, not on quantum field theory because your range is huge. We can start with general theory of relativity and how relativity evolved from classical mechanics and what is string theory a lot. I am sure those who are listening right now would be willing to. Rakesh is saying, thanks for the wonderful talk. One of the doubt for years haunted me a lot in understanding the fundamental gravitational physics. I got the answer from a well-known scientist. So
Thank you. Thank
that
you
is
very much.
wonderful.
I have a suggestion for all the students, since a lot of students are accessing your forum.
Again,
Uh,
sir, one more episode. Requests are coming.
Thank you. So my request is those who are already in research or even not in research, try to access this thing called archive.
Archives, right?
Archive actually a forum where people used to post their recent papers, research findings. Now you go there, there are lots of things like cosmology, quantum cosmology, statistical mechanics, quantum mechanics, quantum gravity, high energy physics, etc. You just click on something, go there, you will see a lot of papers. Now, it may happen that out of 100 papers, you will not understand any of them. But some of the papers, you just try to understand by seeing the subject or maybe by seeing the keywords.
Absolutely,
Try to
absolutely.
read like that. Don't try to mold yourself by reading this melodramatic
Scientific books, right?
science stuffs.
Absolutely.
Go
That
to
is
the
my
real stuffs and understand that.
absolutely. So, sir, I won't take time. It was 1 hour now, 1 hour 21 minutes. So everybody is thinking one more episode, one more episode. Time permits, I will talk to you. And apart from quantum field theory, because your spectrum is huge, we can host something on classical mechanics. Somebody was telling classical mechanics is equally important. That is the foundation, sir. Why don't
Sure,
we look into that?
sure, sure,
So
sure.
he is telling that I studied in a book, but it consists of hypergeometric matrix series and complex sensors. So I cannot understand, and that is why I asked the proof. So,
Yeah, ask you, Prof. So you please, if you are really interested, please forward this question to me. Means
right.
write to me. I will look into your answer surely. Okay.
Somebody asked me this one, sir. Can we generalize Navier-Stokes using quantum?
Excellent question. Answer is no, but partially correct. Means people, my mentor, Professor Shiraz Minwala, tried to Navier-Stokes equation cannot be solved exactly. So he used this technique, Navier-Stokes equation, to solve the fundamentals of gravitational perturbation in the language of fluid mechanics. There,
Oh,
using the perturbation theory, he actually tried to solve the Navier-Stokes equation in the quantum regime up to a certain orders. So it's not completely possible, means non-perturbative result we don't have, but at least perturbative up to certain limit, correct result we have. And this result exactly compatible with the black hole physics, quantum black hole physics. So my
okay.
final answer is we can generalize Navier-Stokes equation for the perturbative quantum field theories.
So those who want Professor Sayantan Chowdhury again to come, please put up your comments. I think sir won't say no, but yes, I have to take up a time and everything on that. So those who wants Professor Chowdhury again to be back on my channel, because you now understand how beautifully, wonderfully, and simplified way he explains. So I think that we can definitely host him, and he would be happy to do that. But for today, sir, thank you very much. Excellent speaking, excellent time, and we will carry on with this, as I was telling to all my viewers. So Rakesh is telling one more one more pure episode on physics mathematics. So he's telling that use of pure physics and mathematics. So I told you, sir, they won't let you go. But anyway, we are running out of time. So yes, please put up the comment once we end this session, that how many of you really want to know. And I'm sure that sir is such a loving person, he won't say no. And we would love to host him. Thank you very much for your excellent explanation. Thank you. So that's a huge
I
round of
I have to thank Shaunak for giving me this opportunity to speak in your forum. Means a lot to me, and we are for students only, na? Means like
absolutely.
students completes us.
Centric,
So
or student centric approach. Right.
yeah,
So thank you, sir, and please stay tuned because next month I am getting somebody reputed scientist on the area of nuclear physics. So if you have question regarding nuclear physics, is a very educated, very senior person, and he would come, and we will again have a session by the end of October. I will announce the date soon. And again, a heartfelt thanks to Professor Chowdhury. And I think that we won't let you go, sir, because there are a lot of subscribers who are constantly commenting me. Let us make up a time in the month of October or November, and we can speak again on a topic, because your explanations with this holding paper, etc., are truly amazing. I really have no words. As I told you, my sole purpose is to educate and educate my people, my subscribers, all my students. Maybe some of them are very senior to me, and you are an excellent source for that. So without further words, I would end the session with a heartfelt thanks. Thank you, sir, very much for being with us.
thank you.
Thank you, sir. Goodbye.
Goodbye.